Tēnā koutou, kia ora koutou katoa, no mai haere mai ki te herenga waka. I'm Professor Margaret Hyland, Deputy Vice-Chancellor of Research here at Te Herenga Waka, and it's my great pleasure to welcome you on this wet winter evening to the inaugural lecture of Ben Ruck, Professor of Physics. Professor Ruck is an outstanding contributor to the academic community. Whether in the teaching, research, engagement, or leadership aspects of his role, he excels. He's an experimental condensed matter physicist, and more of that later. And his work sits at the intersection of curiosity-driven discovery and real-world application. His current research focuses on developing novel materials to solve the limitations facing next-generation superconductors in quantum computing. However, those who know Professor Ruck best will recognize his passions beyond academia, whether it's mountain bike riding through the hills of Wellington or exploring New Zealand's bush and coastlines or Thai kickboxing. Ben tells me that he never had a deliberate career plan as such, but a series of exceptional teachers and guides, including his parents and extended family, offered him the support and time that he needed to grow and develop. And I think we see him paying that forward now for his students and colleagues and collaborators. What he enjoys about his career is the thrill of learning and the excitement that comes with discovering something new. He also finds great pleasure in sharing knowledge with students and watching that aha moment as they grasp complex ideas and their enthusiasm grows. Ben started his academic pursuits studying a double degree in economics and chemistry, but he realized along the way that his interests were really in physics, and he clearly chose the right path. As over the course of his career, Professor Ruck has secured more than 18 million in external research funding as lead investigator. His research programs demonstrate strong ongoing collaboration with the university's Robinson Research Institute, GNS Science, and a wide network of international peers. He also has a passion for applied science. He's engaged with the startup company Liquium Limited, which aims to decarbonize ammonia production using novel catalysts. As a supervisor and mentor, Professor Ruck has guided many postgraduate students to successful completion, with some going on to become academic staff at the university. And he's quick to credit the mentors who shaped his own career, particularly Emeritus Professor Joe Trodahl and his late colleagues, Professor Sir Paul Callahan and Professor Pablo Echegorn. Their influence lives on in Professor Ruck's own generous, thoughtful approach to mentoring. Ben has served as both deputy head and head of the School of Chemical and Physical Sciences, guiding the school through some pretty difficult periods, including over COVID-19 and times of financial strain. He led with empathy, creativity, and tireless dedication, always working to maintain morale and collegiality. As head of school, he led a major overhaul of the university's physics program, one highlight being the development of the new space science major, a forward-looking addition that will help shape future careers in Aotearoa's growing space sector. Beyond the university, he's made significant contributions to the wider physics community. He served as president of the New Zealand Institute of Physics from 2009 to 2011, and apparently is still the reluctant custodian of the Institute's filing cabinet of archives. Offers to take it off his hands are welcome. His commitment to physics education is equally impressive. He's built strong relationships with secondary school physics teachers across Aotearoa, supporting professional development and helping shape curriculum through the work with the New Zealand Qualifications Authority. Professor Ruck embodies the values of Te Herenga Waka, His work contributes in real and tangible ways to our strategic goals in research, in learning and teaching, engagement, and innovation. He's a scholar, a leader, a mentor, and a tireless advocate for the value of physics in society. Tonight, in his inaugural lecture, Ben will share his journey in condensed matter physics, focusing on his recent work that could help enable the next generation of ultra-fast computing. This technology has the potential to significantly reduce the environmental impact of our online activities. I've been really looking forward to this lecture tonight, Ben, and it's a great pleasure to now welcome you to deliver your inaugural lecture.
Oh, thanks so much, Margaret. It's really kind. Made me really nervous now. Kia ora, everybody, and welcome. Thank you very much for coming. And especially welcome to my beautiful wife and wonderful kids, Ariana and Charlie. Thanks, Annie, honey. Okay, so you can see the title up there. So, yeah, we're going to talk a little bit about some of the research stuff we do, but before that, I do want to go through a little bit of a journey talking about some of the people who've influenced me to be here, and that's why I'm standing here in front of you right now. Very first thing, though, going to introduce a list of things that are good. Right. This is important stuff. And as you take it in, it'll be like one of those sort of little tick-the-box thingies, play bingo. We should see all of those here somewhere in the talk tonight. Okay, so what is condensed matter physics? So you're probably all sitting there thinking, well, we all know, because we're just like this guy. We sit there with a condensed matter physics textbook in front of us in bed at night. So this is a real image taken from a British situation comedy, so a sitcom. What's it called? Keeping Up Appearances, I think it was called. And this is the brother or brother-in-law of the fancy person who's always reading something. So obviously condensed matter physics is something that's sort of general interest. Being serious, basically condensed matter physics is the physics of stuff. So everything that's not a gas or a plasma, more or less, falls into the realm of condensed matter physics. So it answers questions like, why is glass let light through? Why do some materials conduct electricity while some don't? And more exotic questions about the stuff that we deal with in our everyday lives. One of the most important examples, of course, that shows the real utility of this branch of physics is that basically all of our electronics is built on discoveries that are made in condensed matter physics laboratories and within the theory of it. So this is an example of the microprocessor out of a computer, so it would fit neatly inside the palm of your hand, no problems. And somehow, using what we know about condensed matter physics, we can put 6 billion transistors on the surface of that, and they all work. And so to do this, you really have to study the way stuff works, all the way down at quantum level. So this is a picture. It's not just frowny faces. So this is a picture of some recent results, and I'm not going to go into the details of what this actually means, but this is recent results that I obtained along with Will, who is sitting over here, and Ted, one of our PhD students who can't be here tonight. So this was from a synchrotron in Sweden. This is probing what the electrons are really doing inside a sort of an exotic material. Okay, so but as promised, I talk a little bit about the journey that took me here. So some of you will recognize where this is. I know someone who does for sure, Mum. So this is the clock tower in the Nine Eye Shopping Centre. So I did most of my growing up just around the corner from there. So lived there with Mum. Mum was still in the same house, just a stone's throw from where that is. And where me and my brothers spent our formative years, weekends in town with Dad, of course, which was also fantastic. We're really lucky to be surrounded by people that gave us a fantastic start in life. Born into a loving family, stable, and that makes a massive difference, right? And I certainly don't remember doing anything to earn that. Like, you just get lucky. also, as I said, there's Dad. And so I made Margaret and Nikki wear the robes tonight for a reason. So this is the front page of my dad's PhD thesis. So, and you notice that it was obtained from here at Victoria University of Wellington. So I'm wearing his robes tonight. So that's the reason. And very proud to be able to do so. Dad's PhD was in the field of zoology, and what he studied was the little tiny fishes that live around the shore. So this gives me an excuse to show a wonderful photo of the Wellington coastline. So this is across Pencarrow. Not only does it show the coastline, but also the orongorongs in the background, so wonderful places to go and explore. So this is the kind of little fishes that Dad studied. We call them cockabullies, which, and someone might correct me later on if I'm wrong about this, but I believe this is sort of a anglicisation of the Maori word for these fishes, which is kind of cool. Dad was pretty good at art, as well as understanding the science behind these things. So these are diagrams, and they're hand-drawn, so taken from his thesis. And they're pretty cool to look at, right? Just illustrating the bone structure of these things. So I grew up surrounded by people that cared about education, cared about scientific stuff, Auntie Chris and Uncle Mike, Mum's cousin Nigel and Beverly. So all of them sort of, they gave us this sort of passion for just understanding the world around us. Moving on to school, so went to Nainai College, so that's the Nainai College crest. I couldn't for the life of me find a better resolution version of it than that, unfortunately, but there it is. And on the other side there, that would be a real challenge if anyone could figure out who that is. So he didn't usually dress like that, but that was my teacher when I was in what was called Form 2 back then, so around about 11 or 12 years old. So that's John Wooten. He also happened to play number 8 for the Wellington rugby team, so he's a very good rugby player. I think this is him in the game where he won the Ranfurly Shield. And something I remember about him is he was the kind of teacher, he was empathetic, he was fantastic with all the students, and he just encouraged you to think. Not necessarily about scientific stuff, about sort of moral questions, all that sort of thing. But he did that with the whole class, and he really respected our ideas. And that is something that really stuck with me. Funnily enough, in the very next classroom, we also had Mike Clamp, who was a current All Black. So, pretty awesome rugby school. Following that, I moved on to this place. So hopefully everybody here recognises that, because we're in this building right now. Okay. So I came here, and as Margaret said, I started off studying chemistry and economics, and they're fantastic subjects, and I really value everything I've learned in those subjects, but ultimately due to, I guess, once again, having fantastic teachers. For example, John, who I see sitting there in the second row. I found my passion for studying physics. So I went on, completed an undergraduate degree. I was quite young, and it showed, and I managed to get through honours as well, even though I swore I was never going to do anything like that. And then I wasn't too sure what to do, but my classmate Sarah said, why don't you go and talk to this guy who you see over on the left-hand side there? So that's pictured much more recently with my colleagues Frank and Simon. So that's Professor Joe Trodell. And he had a PhD position going, and he offered it to me. I wasn't the most worthy member of the class, I think, at that point in time, but I was the most available, so that kind of worked out. But the cool thing is, one of the first things I realised is I didn't really know that much. So despite having, fantastic teachers, and I had learned a lot, but there was a huge amount still to learn. I just realised how much there was. And I immediately picked up the textbook and just started reading and reading and reading, as well as doing my lab work. I found that incredibly valuable. Joe's incredible supervisor, and very privileged I still get to work with him now. He's sick, unfortunately, so it's a real shame that he's not here tonight. But I've had the pleasure of interacting with him ever since, both as a colleague, as him as my mentor, absolutely, and as a friend. He put great faith in me and sent me overseas, which was really good for my development as a scientist. One of the places I went to was Lewis and Clark College for a few months. And this is a small college in Portland, Oregon, so it's built around this beautiful manor house that you can see there. there's a reflecting pool in front of it. If you turn around on the other side of the reflecting pool, then it's sort of lined with trees and it points directly at Mount Hood. So fantastic place to go and spend some time. While I was there, I was working with this guy, Professor John Abley, who you can see driving the boat there. So this is a photo that was taken in 2009 when I was back over in that part of the world on sabbatical. And the rest of the crewmates, so that's his wife Judy there. You can see that we've got a glass of wine. So ticks one of the boxes. You can see the bosun, Ariana, has a bit of a 1,000-yard stare. There's Ariana, my daughter. So she's obviously seen some stuff. And I think Charlie is guilty of dereliction of duty there. So we'll probably find himself in the brig. The person that's missing, of course, is Annie. She took the photo. As a result of that work, so I managed to publish my first paper that came out from work during my PhD. So you can see this is published. This is the first paper I had that I was really sort of the serious contributor to. So it's published along with John and with Joe. So Joe's real first name is Harry, in case anyone's wondering. And also on the list you see Simon Brown, who I also spent some time at the University of New South Wales working with a couple of times there. And Simon I still interact with quite a lot. He's a professor of physics down in Canterbury. And you can see that sort of true to the title, this was about superconductors. So looking at the way superconductors interact with magnetic fields, to be precise. Okay, after I finished my PhD, I went over to this lovely location. So I've been really blessed. I spent a lot of my career in places that have fantastic views. So this is the University of British Columbia in Vancouver, Canada. It's actually pretty massive. So all of that is the university. It occupies a peninsula out in the, out by the sort of harbour entrance in Vancouver. Annie and I lived on campus for most of that time. The campus is really cool. So it's surrounded by forest. You see deer, coyotes at night and stuff like that. I even saw a skunk once. There's bald eagles that nest in those trees that you see along there. And down in the front, you can see a little triangle of sand. So that's called Ruck Beach. You're allowed to go there. You don't even have to wear any clothes at all. But Vancouver can be a little cold, so be warned. I was working with Professor Tom Tichy there. So, and he was also fantastic to work with. Incredibly clever, and also great fun. Always keen on an expedition up into the hills. Always the expeditions ended up taking a lot longer than usual. I never managed to end up stuck in a snow cave with him, but some others did. So, but I definitely remember stumbling through a forest in the pitch black with no headlamps trying to find our way out. But then, huge change happened in our lives, and Ariana came along. She was a little bit smaller when she was born than this picture here, surprisingly enough, but that was a reason to come home to be with family, to be where our roots are. So Ariana was born. This is her with her very, very trusted companion, Eva, our lovely doggy. So that brought us back to Wellington and working on a Foundation for Research, Science and Technology postdoctoral fellowship. I should also mention that was when I really started with the kickboxing. I did manage to train with some friends over in Canada, but I got into it much more solidly when I was back here. So this is the gym, the Muay Thai Institute, but here's one for you, Margaret. At the time, it was actually the Victoria University Kickboxing Club. So this is a successful spin-out company from the university. Something else is kind of handy. So in my very first fight, which wasn't too long before Anna was born, I got knocked out cold. So it's a great start. But on the plus side, not too long after that, I started on the academic staff, so I had to do lecturing. And there's nothing like getting knocked out in front of hundreds of people to get rid of your fear of speaking in public. So no matter how much I screw up the rest of this talk, I'm probably not going to get knocked out. Okay, as I said, I moved into an academic position here, and one of the people that really enabled that for me was Professor Sir Paul Callaghan, so amazing New Zealander. And I had the very great privilege of teaching with him. And teaching with them in first-year courses, which is great, and also in in fourth year quantum mechanics. So this is a slide of, and this is his slides from the 90s that we actually did eventually digitize them, so which is good. But this is from the fourth year quantum mechanics course. If you look closely, and some of you might recognize it, so this is dealing with group theory. So this is mathematical theory, but it's the language you use when you're talking about symmetry. And symmetry is an incredibly powerful idea in physics. So looking at things that you can do to change a system, but leave it invariant, as we say. So things like, really fundamental stuff like the idea that the laws of physics are the same today as what they're going to be tomorrow, which ultimately is where ideas like energy conservation come from. So getting to teach with him, picking up part of a course or half the course that he used to teach, that was a really, really good learning experience for me. And as I say, also teaching first year physics with him, promised I had to show some Olympic weightlifting as well, which was something that I had a great deal of fun doing before I left for Vancouver. Me and my brother Dan as well, and the weightlifting trips were great, weren't they, Dan? Boy, we learned a thing or two on those. But there's some cool physics involved in that as well. As Margaret mentioned, I want to pay special mention to a late colleague, Professor Pablo Echegon. So he was actually appointed in the position that I applied for, and Paul managed to find a sort of a starting out position for me at the same time. So Pablo was absolutely brilliant. It's an incredibly clever physicist. Some of the best insight that I've ever seen. He was also hilarious. So it was just a fantastic guy to be around. Something he really, really liked was this. And he really, really liked it because he was a professor himself. So this is the Peter principle. So this is the idea that anybody in their job, if they're doing their job well, they'll get a promotion. And if they're doing that well, they'll get another promotion. And that keeps going until you reach the point where you're not doing your job very well anymore. So you don't get any more promotions. So in equilibrium, no one actually knows what they're doing. And this really tickled Pablo. He thought that was great. I think it's also a perfect opportunity to sort of to give some thanks to some people. So as Margaret mentioned, I spent some time as head of school, and that's a challenging role. It keeps you especially busy, and it's impossible without support people around you. So I really want to thank this crew. These are people I sort of very directly interacted with in those roles. So Rob, Natalie, Joanne, Patrick, Martin, who was the head of school before me, so I was deputy head of school with him, and the amazing Cara, who's our school manager. Absolutely no reason why I should put you lot under the Peter principle. Okay, so to talk a little bit about the research that we do, and first of all, to sort of put it into context. So we spend a lot of our lives online these days, and more and more and more. So whether that be on Facebook, doing important things, this was on the list, playing video games. A lot of the stuff now, the computing that's driving it is not happening inside your desktop or your laptop. A lot of it is dealt with in big servers. So they look something like this here. So these are great big computing facilities, incredibly powerful, and that's where all the action is taking place when you do a Google search, when you're using AI, all that kind of thing. One of the problems is, though, that these things use an incredible amount of energy. So already something like 5% of the world's electricity goes towards driving our computing, and of course it's growing fast. And things like AI, like Bitcoin and all that sort of stuff, they really, really chew through that energy. So that's a problem. You can see it here. There's this data center. It's built in Sweden, and it's actually quite convenient to build it in the snow. It makes it easier to cool it because it's chewing through so much energy. So this is an example of some of the air conditioning that's associated with it. It's quite good just to open the doors and let in the cold air. So what do we do about this? Well, one of the things we'd like to do is to look for entirely new ways of doing computing. So all the computing we have at the moment is based around this wonderful material, silicon. It operates at room temperature. We'd like to replace that with something different. And one of the best candidates is looking for making computers not out of silicon with conventional transistors, like I mentioned before, 6 billion on a single chip, but replacing that with superconductors. So superconductors are amazing materials that when you make them cold, then they conduct electricity without losing any of the energy. And this graph illustrates some of the potential that they have. So it's a graph of the performance and the power used by not actually data centers in this case, but by supercomputers. So these are the really the most powerful computers in the world. It's missing some of the most powerful ones that have come along a little bit more recently, but these are the most powerful computers in the world. They're the ones that are used for doing the really advanced calculations, like trying to really predict how the climate's going to behave in response to changes in what's in the atmosphere. So you can see that as the performance goes up, the amount of power that they use goes up as well. And to give you a bit of a feeling for that vertical axis there, 1 megawatt, so right in the middle there, that's around about how much you can get out of one of the really big wind turbines. So and this is just for one computer. But much further down is showing what we could achieve if we can properly harness superconducting computing. So it has the potential to be incredibly fast and therefore very powerful. You can do an awful lot of computation, and to do so with very low energy cost. Okay, so just a little bit of background about that then. Superconductors, they're materials that can carry electric current and they don't dissipate any energy in doing so. And they have this other interesting property that if you make a loop of superconductor, and actually as I look at you, John, I remember you were my PhD examiner and you asked me this very basic question to start off my PhD oral exam. And I was flustered and I couldn't come up with the answer, even though it was absolutely trivial based on what I'd done technically. But now I remember that a loop of superconductor traps magnetic flux. So something like this, if you have a superconductor, so that's showing an electric current flowing superconductor from the left there, and it meets a place where the superconductor splits into two arms and forms a loop, and then it joins back together. As the current flows around that loop, then you can have magnetic flux. So bits of magnetic field trapped inside. And one of the amazing things is the amount of magnetic flux. You can't just wind it up and down at will. It can only be fixed chunks. So it's what we call quantized. So discrete amounts. And discrete things are really good for doing computing, like ones and zeros. It's also true that when a single quantum of the flux enters or leaves the loop, it creates a pulse, a voltage pulse, inside the superconductor, right, which will travel down the superconducting wire. So you've got a way for making different loops communicate with each other via these pulses. And these pulses have great properties. They travel incredibly fast, and they can be created and destroyed really quickly. Ideal for doing ultra-fast computing. They're a very well-defined size because of the quantized nature of them. And they travel down the lines without wasting any energy. So this is a pretty good platform to think about doing computing with. And this does indeed exist. Quite closely related to that is something that's coming out now. This is so-called quantum computing. So this is another paradigm shift again. So computing generally is all based on ones and zeros. And you turn them on and off with switches, which is basically what the transistors do. If you use the rules of quantum mechanics, then you can do a different kind of computer where the individual bits inside your computer aren't ones or zeros. They can be some kind of mixture of 1 and 0 at the same time. Right? This is like Schrodinger's cat, where you have a cat which is neither alive nor dead until you go and do some measurements of it. And the world is now developing actual quantum computers. So this is an example of one, and it made the cover of Time magazine. Of course, lots of things make the cover of Time magazine. They're not always good. But this one's pretty exciting. So this beautiful chandelier, it's called a dilution refrigerator. It's something that cools the quantum computer down to the ultra low temperatures, so millikelvins, very close to absolute zero. So absolute zero being about minus 273 degrees C. So it cools them down to being incredibly cold. The quantum computer just sits on the little part down the bottom there. All the rest of it is associated with making it cold and getting the information in and out. And these quantum computers are also based on superconductors, just like on the previous slide. This is taken from the IBM webpage. This is sort of their roadmap for developing these quantum computers. You can see the one in the middle there, which has a person just sort of walking next to it. It's called IBM Quantum System 2. That exists. So that's already built. It's in operation. Pleased to say that thanks to some of my colleagues, our third-year physics students actually access this computer and do calculations on it to demonstrate some of the rules of quantum mechanics. And the rest of it is rapidly being developed. I also want to show you this one. But you'll probably recognize this, right? So this is another quantum computing company. It's called D-Wave Quantum Incorporated. So this is a company that was started in Vancouver, British Columbia. It came out of the University of British Columbia. And it happened to come out right when I was there. So I remember this. It was quite exciting. So they started this quantum computing company. And one of the people that started, and it's still going very strong now, collaborating with Google. One of the people that started this company is Alex Zagoskin. So he's a theoretical physicist, and he's really cool. He looks and acts just like one as well, right? Just like you think a theoretical physicist should act. He wrote this textbook here. And this is a fairly advanced textbook, not surprisingly. So quantum theory of many-body systems. In particular, it's talking about what happens when you get a whole lot of electrons together all interacting with each other, as you have in condensed matter physics systems. Something like inside the book are these diagrams these sketches that Alex himself actually drew. So the first one with the footy player, you see the tackle. That's supposed to represent just a simple interaction of two electrons. But one of the points he's trying to make is if you look lower down, when you get many electrons all interacting together, then things can get much more complicated, and you can get sort of exotic so-called quasi-particles appearing. There's a reason I chose to show this particular picture here. Something that is really important is you notice that on the football jersey is a V, right? This is not a rugby union player, this is a rugby league player. So there we go, the Newcastle Knights. Rugby league tops usually got a V on them. I'm trying not to tear up because I'm looking at the Knights. Getting a little bit closer back towards what we actually do, this is one more quantum computing company. This is SEEC, the QC stands for quantum computing. This is a company that literally, was it today or yesterday, Simon? The announcement came out that they have got a new collaboration with IBM. And you can see the idea is to take the superconducting devices and make them smaller and more energy efficient so that they'll enable like the powering up of these quantum computers. One of the cool things is that this is a company that we actually work with and have had a lot of interactions with. The interactions are based around a long-standing relationship that our colleagues from Robinson Research Institute have had with the parent company, which is called Hypres. So this is based in New York. And the picture there, that's Will, Simon and myself, so out on the edges there. Roger from Wellington Uni Ventures, so this is all at a conference. Jackson, who's also part of our group. And then in the middle, Halima, she's a collaborator of ours from Napoli. And the other guy there is Igor Vernik, so he is the Chief Technical Officer at SEEC. And he's good value, actually. All right, but we don't have ubiquitous use of quantum computers. We don't have ubiquitous use of superconducting technology in data centers and so forth, and that's because there's a bunch of physics and engineering challenges that still need to be met. One of those is learning how to miniaturize these superconducting circuits. So we're nowhere near being able to fit 6 billion of them onto a single chip these days. And all computers have memory. So the information gets shuttled back and forth from where it's being processed and interacting with other data, and then back into memory. So all computers need memory, including superconducting computers. And this memory, it's going to have to work well at low temperatures, and this is a challenge for existing technologies. They don't. It has to be ultra-low power dissipation, and it has to be able to be written and read very, very quickly. Otherwise, all your benefits of shifting to superconducting computing are lost. One of the most promising avenues is to incorporate magnetic materials into superconducting circuits. So, very simple illustration of how that works. This is like a little schematic showing two magnetic layers. One of them has its magnetization pointing upwards. The other one has a magnetization that can be easily switched between up and down. And they're separated by a barrier. The little black lines are supposed to represent wires. The difficulty of passing electric current through this depends on whether the two magnetizations are aligned or anti-aligned. And that's nice. That gives you basically a 1 or a 0. So that's a memory bit. And you can actually buy magnetic memory already, for example, from this company Everspin, although it's not actually suitable for use at cryogenic temperatures. So to give a little bit more weight to this argument that magnetic materials incorporated into superconductors, I've included this paper here. This paper only came across our desks yesterday. I don't for a minute mean to imply that I wrote this talk at the last second. So it's been ready for weeks, trust me. But this is a review of the idea of incorporating magnetic materials into superconducting technologies and saying that it genuinely has shown distinct advantages. Okay, so where do we come in? We're looking at some novel magnetic semiconducting materials. So we're trying to use magnetic materials like some other groups are using, but the magnetic materials we're using are a little bit different from most. And the reason they're different is because they're actually semiconducting, not metallic. So this is a picture of the research group. And yeah, it's a mixture of academics, emeritus staff, colleagues from School of Chemical and Physical Sciences, from Robinson Research Institute, from Canterbury and Otago University. Includes the wonderful students who are the ones that really do all the work, of course. And they're the ones that keep you young and really wanting to come to work each day. For some reason, it was a good idea to take a photo with the projector turned on. And we're very lucky. We're funded to do this research at the moment from MB, so through the Endeavour Fund, which actually allows you to have a large research group which is needed to make any progress in a field like this. Okay, so the materials we're looking at are called the rare earth nitrides. And so they're what you get when you mix one of the rare earth elements, and rare earth elements have made the news quite a bit recently. Donald Trump seems to like them. But I'd be entertained to see if he could place them on this periodic table here. They're these ones that hang out down the bottom there. Right? And they're characterized, for those who have done some chemistry or some atomic physics, by filling the 4f orbital. So one of the orbitals around the nucleus, they're characterized by filling that. And they give the rare earth metals quite strong magnetic properties. And what we do is we alloy them with nitrogen. So good old nitrogen, in the air that we're breathing right now, most of it. And it forms into a crystal structure like this. So each of the green blobs might represent a nitrogen atom, and each of the white blobs, one of the rare earth atoms, and we can choose from across the series, and we get different magnetic properties as we do so. Interesting, this is God's preferred crystal structure, of course. I say that because it's the one I'm most familiar with. It also happens to be the same crystal structure as good old table salt, so sodium chloride. How do we make them? So you have to make them in a really, really clean environment, and for that we use a molecular beam epitaxy chamber. So you would have seen that come up briefly in the video that you saw just before. So this is the MBE chamber here. It's like an inside-out spaceship. So the vacuum is on the inside. This gives us an incredibly clean environment to work in. And what you do is you take some of the rare earth metals and you heat them up so hot that they start to evaporate. And they land on a substrate, so some flat material, and you end up with a very, very thin layer. It's kind of like huffing on a mirror, except it doesn't evaporate away again when you're finished. So you evaporate the rare earth, and you have to do it with some nitrogen around. Those two things react together, and they give you the rare earth nitride. So this is a chemical compound. Oopsie daisy. What makes them interesting? Well, the first thing is that nitrogen steals the electrons from the rare earths. It steals the electrons that made them metals. It steals the electrons that conduct electricity. And the cool thing about that is that then you no longer have metals. Oh, I like that picture there. That's Orion, by the way, so he's named after the stars. But it turns them into semiconductors. And I like this guy too, conductor. I like how he looks like he's casting a spell. He should have my robes, I guess. Okay, so you transform them from a metal to a semiconductor. Semiconductors are really good because you can control the way they conduct electricity very well. They also have, and I'll put this into a bit of context in just a moment, lots of orbital angular momentum associated with those electrons orbiting around the nucleus. And they carry this property called spin, and in the rare earths, there's lots of it. So the idea is a bit like this. This is the sun, the Earth going around it, the Earth orbiting around the sun, that's orbital angular momentum. But the Earth also spins around its own axis. That's like spin angular momentum. So you've got a combination of two different sources of angular momentum in these materials. That diagram is not to scale. Also, there's only one Earth, not four. But you can have lots of electrons, of course. Okay, one of the interesting things, due to the rules of quantum mechanics, the electrons in these materials like to line their spins up all pointing in the same direction. The diagram's kind of convenient there. You can see all of the Earths are spinning in the same sense. So that's what makes it magnetic. It also turns out that a lot of the time in these materials, the spin likes to line up opposite to the orbit. So that doesn't match the diagram here. The diagram here has everything is rotating clockwise if you look from, in this case, from the bottom, I think. But in these materials, the spin part is the opposite sense to the orbital part. So you get these sort of competing sort of effects. Furthermore, if you put an external magnetic field, then it likes to line up the sum of the spin and the orbital. And that will depend on which one of the two happens to be larger. And that varies as you go across the rare earth series. So I'm condensing many years of work that we've done on these materials into one slide here. But the important point is that you get sort of competing effects in these materials, and that's where you get interesting physics. You can do things like take the spins and wind them up by applying an external electric field when you take two different rare earth nitrides and put them next to each other. To be able to use these things, you really have to understand them in detail. So we've done a lot of work with synchrotrons around the world. So this is a synchrotron in Grenoble in France. So once again, another beautiful place to go. So that's the synchrotron there. It's basically a giant light bulb. It produces light all the way from the infrared to X-rays. And we in particular use the X-rays when we go there to study what's going on inside these materials and to understand what those spins and those orbits are really doing and how they're talking to each other. Just in the back, the sort of domey building, that's a nuclear reactor too, where you can do measurements with neutrons. And just for the sake of it, showing what they look like on the inside, this is from our recent trip to Sweden. This is an electron energy analyzer that you can see there, so this beautiful shiny dome. One of the things I liked about it the most is we took a picture there, so that's me and Will and Ted reflected in the shiny electron analyzer. I especially like the fact that Ted has this sort of alien-shaped head that looks like one of those medieval paintings. So Ted doesn't look like that in real life. I'm pleased to say we've actually made a lot of progress now taking these materials and turning them into real sort of proof of concept or test devices. So this is showing, us taking these materials, incorporating them with superconductors and forming them into, microscopic sized devices. So you can see the one over in the sort of top right there. It's 6 micrometers by 6 micrometers. And these things are starting to show some real promise to give some really interesting and exotic physics that you can't get if you don't put these sort of weird materials inside your superconducting Josephson junctions, as they're called. This is some of the results. I'm not going to take any time to try and explain exactly what they mean. We're measuring the voltage and the current that flows in response to an applied voltage. One of the things I do want to emphasize, though, is that that some of these measurements, the ones shown in blue there, they've been taken at pretty low temperatures, 14 millikelvin. All right, so getting to the end now, and I realise I'm pretty much standing between you and the refreshments, which is a dangerous place to be. It's like being between a hippo and the water or something like that, right? But just a few quick notes about this. Like, what is physics good for in general? Not just condensed matter physics, but the whole thing. And you can apply this to quite a few of the sciences as well, of course. So I like this. This comes from Richard Feynman, who's incredibly famous physicist, a bit of a dick, but I guess it was different times. But he came with this, like, how do you go about solving a problem? And of course, the world is faced with some really important problems that we need to figure out how to solve. So step number one, you really have to define your problem, right? You write it down. So you have to know in detail what you're trying to solve. Step number two, and this works, right? It's a genuine way to solve problems. Of course, it might be skipping a few steps. There might be a bit of active stuff that has to take place. One of the cool things, though, is that you can get better at this. So you can get better at solving problems by solving problems. And studying physics is a fantastic way to do that. So you develop critical thinking, problem-solving skills. The other thing I like about this is that I think we do live in a bit of an age where it's quite easy to push simple solutions for complicated problems, and they don't work. This is a bit of an antidote to that, I think. And it's applicable in all these really important fields. For example, designing these. Somewhere in the front row might recognise this. Beautiful zeroed mountain bike made by a company based here in Wellington. So zeroed mountain bikes, and photographed up on the hills above Days Bay in the beautiful beech forest there. Some cool physics goes into those things to make them stay on the ground. But it doesn't just have to be for the problems you can solve and the technologies that you can develop. So maybe you just want to understand how this thing worked. And it baffles me, right? How can you create a living creature that big and it still actually operates? How did it bend its head down to take a drink without the sort of enormous blood pressure that it must have had sort of blowing all its blood vessels? How did it lay its eggs? Apparently mating could have been entertaining, right? So I quite like this quote as well. So it comes from back in the sort of 60s or something like that, or maybe even earlier, when they were producing one of these big accelerator facilities where they were going to probe just the fundamental laws of physics. At scales below anything that we can really hope to utilize anytime soon. And they said, well, how is it going to help us defend our country if we fund this thing? And the director said, well, it's not. But this fundamental knowledge, it makes the country worth more, which is pretty cool. I couldn't squeeze it in, but I couldn't skip it out, right? So I hope I haven't gone too far over time. Thank you so much, everybody, for coming. Thank you to all the people that I've worked with. Really, really appreciate it. Cheers all.
Tēnā koutou, tēnā koutou, tēnā tātou katoa. I'm Professor Nikki Nelson and I'm the Dean of Science and Engineering, and it's my extreme privilege to be doing this vote of thanks for Ben. I'm not sure if I'm the hippopotamus now, keeping us away, but anyway. So I've got this speech written out, and and thank you, Margaret, for inviting us to this event and for hosting us. So Professor Ben Ruck, really pleased that you've made it to the step and are able to talk to us today. I had this whole speech written out, but I wanted to just make a couple of observations to start with. Are you getting your research funding from all the advertising you're doing here today? From how many quantum computing, anyway, and how did you squeeze in so many dad jokes? Well, welcome to your family. I know you've got your mum here, yes, and Ian and Wilma, and your Auntie Chris and Uncle Mike, biology teachers, and Annie and Ariana and Charlie. So welcome to you guys. I know that Ben got here because of you guys, so thank you for all your support there. And I also want to note all the grad students that are here from Ben's group, past and present, because you're the reason that he's got so much to talk about as well. We fully acknowledge that. So really fantastic talk, Ben. Thank you so much. I feel like I've been in a lecture somewhat, learnt a lot, been exposed to an outreach on why I should do physics kind of expose. I think we could capture some of that in some of how we could get future students for the career pathways sort of thing. So lots of possibilities for you in your post-head of school time. I knew Ben as a former head of school when I was a head of school, and then as a line manager as dean. And Ben is amazing in the way that he handles things. He's embodies empathy and advocacy for his team, really calm under pressure through the COVID times. He's an amazing colleague to work with. And so I'm really, really pleased to be up here to celebrate your being a professor, but also just because we kind of have been through some of those times together, and I know how hard you worked for your team, and I wanted to say thank you. I don't feel like I've got anything more to say here other than we're going to have refreshments next door with Ben, and please feel welcome to come and chat with him and catch up with him, especially with those that you don't see very often. Don't just escape out the door, come and make the time, because it's a very special time for Ben and his family. So thank you very much for an amazing talk, and let's just get on with celebrating it.
Thanks, Nick.